All right. Okay, this topic is guaranteed to come up again. It's a really important one. You saw it last year. It got introduced in 8th grade math, but we're going to really dive into it today. So I can calculate the average rate of change, write the word change right here, and interpret its meaning. So, thank you very much. Okay, rates and interpreting their meaning are about half of what calculus is. So again, we're going to do the quick draw at the end to make sure everybody's getting used to this. So I'm hoping somebody in here knows this. When we hear the word rate, we should automatically think, Luke?
Ratio.
You could, but not in this case. Slope. Okay? When somebody says rate in a math class, you should automatically think that a graphic representation of that is slope. It's how steep something is. Okay? So the average rate of change of a function is the change in y over the change in x. Because remember, when we're talking about slope, it's the rise over the run. It's the change in the y's over the change in the x's. So this is like that y2 minus y1 over x2 minus x1 stuff. And we're going to see that again in just a second. So another word for difference, so when we say difference in y's over the difference in x's, okay, is we use a lot of Greek letters in math. So the Greek letter that we use for difference is the Greek letter delta. It looks like this. It looks like a triangle. Okay? So the formulas that we use below, some of these, they should just remind you of a slope formula. So when we say average rate of change, which a lot of times I'm just going to abbreviate and just say AROC instead of saying average rate of change. It's a little bit quicker. This right here is delta y over delta x. Delta, if you hear somebody say this, and you'll hear lots of people do this in business and stuff like that, they'll say, hey, what's the delta? When they say delta, they just mean what's the difference? It's just a fancy, smart way of saying what's the difference. So the difference in y's over the difference in x's. Delta y over delta x. That's y2 minus y1 over x2 minus x1. Better yet, in function notation, because we use functions so much in math, and they contain a whole bunch of information in a very compact form, it would be better if we thought of it this way. So this is going to be x2 minus x1 on the bottom, and on the top it's just f of x2 minus f of x1. So remember, f of x is the same as y. So all we've done in this little formula on the end of this box is just replace y2 and y1 with f of x2 and f of x1. All we need to know is, hey, what are my x values? Where are you interested in finding the average rate of change? And then I'll go find all the other stuff from the function. I know I need to find y's, and I'm going to find that from a function. So if we want to find the average rate of change for this function on this interval, now it's important to realize that when we talk about average rate of change, we're talking about how are things changing on an interval on the x-axis. So when we say from 0 to 2, it's not from the point 0, 2, it's from 0 on the x-axis to 2 on the x-axis. So we want to know what this slope is right here. Now we could count that, which I suppose we'll do in a minute, but this is the formula. So we're going to take x1 and x2 and let's plug it into the formula. So this is going to be x2 minus x1, x2, x1. So here's what we've got. This is going to be a 2 minus 1. Or sorry, 2 minus 0. 2 minus 0. And this is going to be f of 2 minus f of 0. Now, the reason why I like this better is because, you only have to know two things. You need to know the endpoints on the interval on which you want to find the average rate of change. If you want to go from 0 to 2, you do 2 minus 0 on the bottom, and then you plug those numbers into the function on the top. It's not something different that you're finding on the top. Okay, it's not something weird. It's directly related to the x value that's below. So if we said I want to do from 1 to 5, 5 minus 1, f of 5 minus f of 1. Okay, so it's just a nice convenient way of keeping track of stuff like that. So on the bottom, I'm going to have 2 minus 0. We'll simplify that in just a second. On the top, I could plug it in if I didn't have a graph, but I do have a graph. The point happens to be, let's see, plug in a 2, I get out a 3. So this is going to be 3. Minus f of 0. F of 0 is 0, 1. So I end up with a 2 on the top I end up with a 2 on the bottom, and I end up with a 1 for an answer. So that is the average rate of change. Now, instead of saying rate, what did we just say you could say? You could say A-rock. What else should somebody think when we think rate?
Slope.
Slope. This is the average slope. Now take a look at this. This is not sloped like a slope of 1. First of all, it does look like a slope of 1. It's going up from left to right, perfect 45-degree angle. But it's certainly not sloped like that here. It's pretty flat right here. Down here, it's going down. Okay, it's decreasing. Okay, here it's going up quite a bit faster. It's steeper. We are talking about the average slope on that entire interval. It doesn't mean it has that same slope everywhere. It just means that's the average slope. On average, that's what's happening. Okay, so the average rate of change is also called the slope of the secant. And the reason we call it a slope of a secant is a secant line is a line that crosses through a curve in more than one place. Okay, so it crosses to the two of those places. We also call it the slope of the secant. You'll hear it phrased both ways. So we're going to come down here and we're going to take a look at a couple of numeric examples. It says find the AROC, find the average rate of change for the specified interval and interpret its meaning. So this is where we stop and think about, hey, what does this actually mean? And if you label things, that's going to make a lot more sense. So here's the deal. The per capita consumption of breakfast cereal is shown below. Find the average rate of change from 1992 to 1995 and interpret its meaning. And the first thing is this. Hint, what does the 5 represent? What does that 5 represent? I want you to think. Don't let somebody else figure it out for you. Pretend this was a test. It's an easy question, but you got to think about it for a second. Caleb, what does it mean? 1995. It does. That's all it means, 1995. Because over here it tells you what the guide is. This happens all the time when we're collapsing data. We don't want to do 1990, 1991, 1992. Why work with gigantic numbers when you can just kind of take things and lop off the first part of it? Everything here is in the 1990s. So 0 represents 1990, 91, 92, and so forth. That's what it represents. So it represents 1995. So now let's figure out the average rate of change from 1992 to 1995. So what we're going to use is 1995 data, and we're going to compare it to 1992 data. So here's the average rate of change calculation. This is like x1, and this is like x2. So on the bottom, we're going to do 5 minus 2. On the top, we're going to do the function value for x2, which is, I'm pointing at it. Oh, thank you very much. I appreciate that. Just bailing me out, okay? Throwing me a freaking bone. 17.1 minus the function value at x1, or you could call it y1 if you wanted to, 16.6. So we're going to do 17.1 minus 16.6. I end up with, tell me if I'm wrong, 0.5, right? Then on the bottom, I end up with a 3. So I end up with, if I throw that into a calculator, let's see, I get, is it 0.16 repeated? Is that what it is? Am I right about that? Okay. I didn't even have a calculator for that. Okay. No applause, no nothing. Okay. So we get this. 0.16. Yeah, too late. Okay, looks like that. What does that mean? Stop and think, because here's what's going to happen. Now, this will happen for a lot of you. You're taking AP, this AP Geography. You have something called an FRQ, free response question. You have to build your own response. So when you get something like this, you've got to think about it. So there was a hint. Couple of hints. That R means something. What's the R and AROC stand for? Yeah.
Rate.
Rate, which means slope. This is a slope. Wait a minute, you got this beat into your head for a couple of years now. Slope is a fraction that represents how steep a line is and in which direction it slants. The sign of the slope tells you which direction it slants, and the number tells you how steep it is. Big numbers are really steep, small numbers are really shallow. The other hint was this: labels. What goes on the top? Dane.
Like the cereal thing.
The cereal thing. What's the cereal thing? Consumption in pounds. So I'm going to write LBS on the top, and we said slope was a fraction, right? You can make any number a fraction by putting it over a 1. 1 what? Do not let somebody else do the thinking and learning for you. It's right up there. Look at it. I'm hoping just half of you are bashful. Y is on the top, X is on the bottom. You can see where we grab that data. What label goes on the bottom? Angela? Years. So, what does this mean? Gosh, they are noisy today. Is it the freaking hats? What does it mean? If you had to explain to somebody, say you worked for a company and you had to do a calculation like this, and you needed to explain to the boss of the cereal company, hey, this is what we think we ought to do. Sai?
Every year, the cereal consumption goes up 0.16 in pounds.
Okay, goes up about, that's a sixth of a pound per year. Now, I'm not sure if this is in millions of pounds or something like that. Maybe that's per person. Okay. Per capita. Ooh, wait, what does per capita mean? Come on, geography students. Per capita? Per person. Per person. So that's exactly what it means. So a little bit of background knowledge, about a little bit of reading the details. This is about 1/6 of a pound per person. So are people eating more or less?
More.
Okay, people are eating about 1/6 of a pound more every single year. That's what that means. That's the interpretation. You want to write that down? Okay. If you need to, grab your calculator. Okay. I have to pull up my newer one because my old one doesn't do this. Okay. So if I tried this, I'm going to go back to the home screen. And I hit math, change that to a fraction. Ooh, it does. That's pretty cool. There's enough. Changes it to 1/6. So consumption is going up by 1/6 of a pound every year. Everybody good? Okay, next one. Height of an object thrown straight up is shown in the table. Find the average rate of change from 1 second to 2 seconds and interpret its meaning. From 1 second to 2 seconds. So got a lot of information here. Seconds, and then we've got height, we've got it in feet, so we've got everything we need there. Okay, I'm going to put a subtraction problem on the top and the bottom. And I'm going to ask Hannah, what goes on the bottom? It is x2 minus x1. What is x2 in this case? It is. We're actually talking about time 1 and time 2. So time 2 is 2 seconds. Time 1 is 1 second. And then I need f of 2 minus f of 1. What's the function value at 2? Function value at 2, 152. Function value at 1, 162. So here's what we got. We got, let's see, at 2 seconds, this is going to be 152. 1 second, 162. So I end up with, let's see, negative 10 over 1. Just negative 10.
Very important.
What? What does that mean? I'll have to ask Luke because he's getting something out. Hopefully he's got something for everybody.
Nope.
Oh, Luke, what does that mean?
It means the
changed 10 feet.
Say it again.
Declined 10
Dane.
The object is going down at 10 feet per second.
Okay. This was measured in feet. This was measured in seconds. So the fact that it's negative 10 feet per second, we could say that's its velocity. That would take care of it. If we say down 10 feet per second, the negative takes care of the down part. It's a little bit more instructive as far as what's going on in the situation. Okay, everybody good there? Okay. I'm looking at that, and do you notice anything a little weird about this? The data? Where was it at 0 seconds? Okay, what must this have looked like? Picture this in your mind. What must this have looked like? To get that data, yeah. Yeah, it did, but, yeah.
Would it be like someone's throwing it?
Someone is throwing it, but for it to be 140 feet off the ground to start with, yeah.
You go on top of a building, you just throw it up.
Building or a cliff. So we're 140 feet up, then we throw it up, and then it goes like this. Okay, that must be what it's like. A little bit of a unique problem. Flip the page over.
Thanks.
Okay.
Yeah, they put the object.
Joe is visiting the Eiffel Tower in Paris. Anybody been to the Eiffel Tower in Paris? Ooh, wow. No? Oh, I have. I'll have to show you some pictures. Let's see. He accidentally drops his camera. His camera's height is graph. Use the graph to estimate the average rate of change of the camera from 4 to 7 seconds and interpret its meaning. That's great. Okay.
Wow.
How about we just interpret its meaning once? Okay. 4 seconds. 7 seconds.
650.
Abby, what goes on the bottom of this? It is seconds. Perfect. Okay. Megan, what label goes on the top? Height in feet. So we'll put the actual measurement there. What numbers go on the bottom, Samara? It's a little subtraction problem.
Yeah, it would be 7 minus 4.
Perfect. 7 minus 4. It's always x2 minus x1. It's the second one minus the first one. And then we're going to need to subtract some heights here. Andy, what's the height that corresponds to 7, roughly? It's a weird scale. What is it?
100.
Yeah. If this is 150 and we divide this into 3 equal pieces, each one of the marks represents 50. So this is going to be 100. So it's going to be 100 right there. And then, am I right about 650 on this one?
Yes.
650 here. So that's going to be negative 550 divided by 3. We're going to throw that in the calculator and we're going to end up with 183.3 repeated. And that would be feet per second. Now, I've missed something here. I can correct it in one of 2 ways. What did I miss? What did I miss? Colson.
You dropped the negative.
I dropped the negative. I can take care of that by putting a negative on there. Or what else could I do? Falling which way? Down.
Wait, can you follow up?
Yeah.
Okay. Technically, suppose you could. Okay. We could say moving up.
Oh, okay.
Okay. Then Dane's head doesn't explode. You could say that, or you could say traveling at a rate of negative 183.3 feet per second. Okay. All right, we good there?
Fun. Yes, sir.
Okay, grab your calculator.
No.
I'm going to shrink this down. Grab your calculator.
Wow, 2x. Sounds magical. Regular x. What x?
Okay. Let's see. I think I can do
Graph.
this one.
Wow.
Shrink that down. I'm going to reset the calculator. Come on.
This is really hard. 2, 4, 6, 8, 7.
We'll just get rid of that. Okay, everybody watch. If you haven't done this before, we can make this really easy. We've got to complete all of these tables. So I'm going to type in, I'm going to clear this, and I'm going to do 2x. Then I'm going to do x squared. And then I'm going to do 2 raised to the x. Everybody got those? Okay, mine looks crappy, but it's still going to work. Anybody know how the quickest way to fill all of these in?
Graph it.
Dane?
Do you square all of them?
No.
Oh.
Yeah.
Would it be second graph?
Second graph. Second graph is the table. Would you hit second table?
Whoa.
And then if you go to right here, there are all the values for the first two. So I'm going to fill in the first one. So this is going to be -4, -2, 0, 2, 4, 6, 8, 10. Slide over to the next one. Not that these would be that hard because they're parent graphs. They'd be pretty easy. And then there's the last one. I'm going to write that one as 1/4, 1/2. So the table is really cool. You can find all of those values really quickly. Okay, now if you'll remember, you actually did an exploration like this earlier well, let's see, it would have been about halfway through secondary one. Would have been about halfway through last year. Okay, does everybody have them?
Yeah.
Okay, before we do the other ones, because the other ones are just average rate of change calculations. We're going to have, I think, 9 calculations to do altogether, but I want you to watch. Okay, if I just hit graph, okay, so this is actually, I'm going to hit the window. This is that it's 200 tall and it only goes over to 10. So if I hit graph again, here's the deal. This one is the linear one. That's the first one. This one is the parabola. And this one is the exponential. And do you remember this story last year, like 1 grain of rice, and when we did the exponential stuff?
Yes.
Exponentials grow unbelievably fast. They have huge rates of change when we get out near the ends, out near positive infinity. So when you come back to do these problems right here, I'm going to set up a couple of these, and then we're going to go ahead and do them. We're only going to do this for 2 intervals. So for f, here's what we're going to do. This is going to be 0 minus -2. And on the top, I'm going to find f of 0, which is 0, minus f of -2, which is -4, which ends up being a 4 on the top and a 2 on the bottom, and I end up with a 2. So that is the average rate of change between those 2 points on that interval.
Mr. Laws?
Yep.
Hey, will you send Angela Dewey to the attendant's office for a minute?
Yep.
Thank you.
Just in case. Just in case. Here's the thing. Okay, take a look. Why should this not be a surprise? Yeah. Because it's a line. Its slope is always going to be 2x, or 2. Whenever we find a rate of change, we're finding a slope. So guess what it's going to be on this one? Just for the fun of it, let's check. 5 minus 3. F of 5 minus f of 3. It's going to be a 2 on the bottom. Let's see, f of 5. That's a 10. F of 3, that's a 6. Lo and behold, 4 over 2 is 2 again. Okay, next one. We're going to find the average rate of change for g of x. So it's on negative 2 to 0. So that's going to be 0 minus minus 2. And it's going to be g of 0 minus g of negative 2. So g of 0 right here. Whoops, this should have a g on it, shouldn't it? And this should have an h on it. Sorry about that. Everybody catch that?
Should have an H.
G, and this should have an h. Okay. So this is going to be 0 is 0. Negative 2 is 4. So this is going to be negative 4 over 2. So that's going to be negative 2. Right about that?
Yeah.
Okay. What does that mean about the graph? What does negative 2 for an average rate of change mean about the graph on that interval?
It's like
Lizzie?
Well, the slope right there is negative.
It's going down. Yeah, pretty steep on average. Slope of negative 2. Okay, let's do h. I'm going to change colors here. So again, it's going to be 0 minus minus 2. And then I need h of 0 minus h of negative 2. So let's see what we get here. Bottom's going to be a 2 again. So I need h of 0, which is 1, minus h of negative 2. Ooh, that's nasty. 1/4. 1 minus a fourth is 3/4. Divided by 2, or better yet, divided by 2 over 1. I flip the fraction over. Multiplied by the reciprocal, I get 3/8. What does that mean? What does that mean about the graph? There are two things that a rate or a slope would tell you. Dave,
the direction and what way.
is it going up or down?
Yeah, that and how steep it is.
Okay, is it going up or down?
Up.
Up. Very steep?
No.
No, because it only rises every 3 for every 8 that it goes over. It would be about like that. That's what it would mean. Okay, can you find, let's see, this would be 5 minus 3, g of 5 minus g of 3. And the last one would be, oops, need to change colors here. The last one would be 5 minus 3, and this would be h of 5 minus h of 3, and interpret each one of those. We can do that? Pretty easy? Okay.